Swayam Prabha, free DTH channel for education.
Now next one, we are going to write, we are going to see some of the important concepts of the second order linear ODE. So one is called superposition principle or linearity principle. Another is called some theorems and then deduction of order elements. Okay, so let us see that. So first one, let us see the examples. Okay, let us see this problem. Y double dash plus y equal to 0. Then we are going to see what are the solution is going to be possible. Okay, so y double dash plus y equal to 0. Let us take this problem. Y double dash plus y equal to 0. Okay. So I'm not saying anything about this one. Okay, I'm just going to get a trial solution only. Okay, I'm not saying this is the one which we always apply, but I'm going to use a trial solution. For example, I'm going to assume, okay, for example, if I in the earlier one we used something like mx we have used. Okay, suppose you are using something like the earlier one we used something. Now here we are going to check some trial solution. You can check anything. Suppose you are substituting e power x. Okay, you take any trial solution. Okay, take anything. So you check it whether it is going to satisfy. So y equal to e power x. Okay, then if you substitute it over here, this is going to become like again e power x. Again e power x is going to come. Okay, y dash is going to be e power x. Y double dash is also going to be e power x. So if you substitute it here, this is going to become like e power x plus e power x equal to 0 is going to come. Therefore, it is not true. So you can take some other, for example, cos x sin x you can take. So I'm going to take sin x, y equal to sin x. Some known function I'm taking. You can take some other function. Let's take x equal to. Then you can substitute it here. This is going to become like y is going to become x, but y dash is going to be 0. Therefore, it is not going to be. Similarly, you can try different solution. So one such is I'm trying sin x is going to be there. So in this case, y dash is going to become like minus plus cos x, okay, and y double dash is going to become like minus sin x, okay. So you can substitute it here. So this is going to become like minus sin x plus sin x. So the both are going to get cancelled. So we are going to get 0. Therefore, it is going to satisfy. Therefore, y equal to sin x is a solution. Okay, y equal to sin x is a solution for this problem. Now, suppose I take y equal to cos x. Okay, if I take y equal to cos x, so let me say this is the first one I'm going to attain y1 equal to sin x. Suppose I take second one y2 equal to cos x. Okay, so if I substitute the same thing over here, that is going to become like, in this case, y2 dash is going to become like minus sin x, and y2 double dash is going to become like minus cos x. So once again, if I add these two, it is going to become like cos x minus cos x plus cos x is going to come. Okay, therefore again get cancelled, this is going to become 0. Therefore, y2 is also a solution. So that means you got y1 is also a solution, y2 is also a solution. Now instead of that, suppose I try something different. Let's take y equal to 2 sin x. Okay. So in this case, what is going to come? Again, the same thing. Y dash is going to become like 2 cos x is going to come. Y double dash is going to become like minus 2 sin x is going to come. Therefore, if I substitute it here, minus 2 sin x plus 2 sin x is going to get cancelled. Therefore, it is going to be that. Similarly, you can take y2 equal to some 3 cos x. Okay, y equal to 3 cos x. If you take, same thing is going to happen. Now again, okay, if I take y equal to 3 cos x, going to be satisfied. Now if I take both things together, y equal to 2 cos x plus 3 sin x, something different. Okay, 2 cos x plus 3 sin x, or 3 cos x 2 sin x, some combination you take. Again, you are going to check whether it is going to satisfy. So y dash is equal to, it is going to become like 2 minus 2 sin x, okay, plus 3 cos x, and y double dash is going to become like minus 2 cos x minus 3 sin x is going to come. So again, if you add these two together, this term and this term, this is going to cancel out each other. Therefore, this is going to be satisfied. So in general, you don't need even 2. You put anything constant, c1 and c2. Okay, c1 cos x plus c2 sin x. Then this is going to become like minus c1 sin x. This is going to become like c2 cos x. And here it is going to become like minus c1 sin x. This is going to become like minus c2 sin x. So this is c1 cos x, c2 sin x. So these two are going to get cancelled. So therefore, this is also going to satisfy. So that means if you have one solution and if you multiply with any constant, that is also going to be a solution of that problem. Okay, it's also going to be a solution. Also, if I substitute y equal to 0, that is a trivial solution. Okay, mostly we are not interested in the trivial solution. So trivial solution is y equal to 0 is always satisfied. So y equal to 0 is a trivial solution. Okay. Now what this theorem is going to say, this is called superposition principle. That's what we are already did. Suppose y1 and y2 are two solutions of the homogeneous second order ODE. Okay, this problem. Let's take this problem. Okay, not the non-homogeneous one. We are going to take only homogeneous ODE. Homogeneous ODE. Okay, in homogeneous ODE, I'm going to take this one. So y plus p of x into y dash plus q of x equal to q of x into y equal to 0. Okay, so in this case, what I'm going to have, suppose y1 is a solution for this one. Okay, if y1 is a solution and y2 is another solution, then c1 into y1 plus c2 into y2 is also a solution for this one. If it is, this is only true for linear ODE. Okay, so you should be very careful. So for example, we can verify that. What we are going to verify is that we are going to do that. So for example, I can just substitute over here. Since y1 is a solution, I can put y1 double dash plus p of x into y1 dash plus q of x into y1 is going to be 0 because of y1 is a solution. Now y2 is also a solution, therefore y2 double dash plus p of x into y2 dash plus q of x into y2 equal to 0 is going to be there. Okay. Now if I multiply by c1, this is going to be a solution. Okay, I'm just multiplying here c1, c1, c1. Here I'm multiplying by c2, c2, c2. Okay. Now sum these together. Therefore, this is going to become like c1 into y1 double dash plus c1. C1 y1 double dash. Okay. Plus c2 y2 double dash. Okay. Plus p of x into c1 y1 dash plus c2 y2 dash plus q of x into c1 y1 plus c2 y2 equal to 0. So I'm going to denote y equal to, suppose I write it as y equal to y1 c1 y1 dash c1 y1, okay, c1 y1 plus c2 y2. Then this is going to be, I can just use that over here. So y dash is going to become like c1 y1 dash plus c2 y2 dash. Okay, this is going to become like y dash. Okay, this is going to be y. And this is going to become like y double dash. So therefore, what you are going to get? You are going to get c1. You are going to get y double dash. This is going to be there. Y double dash plus p of x into y dash is going to be there. Therefore, what you are going to get? You are going to get. This is going to be satisfied. So this is called superposition principle. That what is it meaning is that if y1 and y2 are solution, in c1 y1 and plus c2 y2, any linear combination you take it, that is also going to be a solution of the second order ODE. Okay. So this result need not hold for non-homogeneous ODE. For example, you can consider y double dash plus y equal to 1, and you can take y1 equal to sin x. Okay, so let me take one. Y2 I don't know. Y2 I'm not giving here. Just I'm taking only y1 and then going to check whether it is going to be there or not. So for example, let us take this problem. So the problem is that y double dash plus y equal to 1. Okay, y double dash plus y equal to 1. Okay, so if I take let's consider this problem. Y double dash plus y equal to 0. For that, I know sin x is a solution. Okay, y equal to sin x is a solution. So 1. Let's see whether this is going to satisfy the principle. Okay, it will not satisfy. So this is going to be there. So let us consider this problem. Okay, this is going to be like you can take y1 equal to 1 plus sin x. Whether that is going to be a solution or not, let us verify. Okay, so let us take y equal to 1 plus sin x. Okay. Then this is going to become like y dash is going to become like minus cos plus cos x, okay, and y double dash is going to become like minus sin x. Therefore, you are going to substitute it over here. This is going to become like minus sin x plus 1 plus sin x equal to, this is going to cancel, so you are going to get 1. Therefore, this is satisfied. So y equal to 1 plus sin x is a solution. Now we are going to check whether if I multiply by some c1 also it is going to be solution or not. Let us verify that. So in this case, what is it going to come? So this is going to come like let's take y equal to, let's take 2 into 1 plus sin x. Okay, or in general I will take it like c into 1 plus sin x. Okay, in general I can take c also. So c into 1 plus sin x I will take it. Then y dash is going to become like, this is going to become like minus plus c cos x is going to come. Okay, y double dash is going to become like minus c sin x is going to come. Okay, so if I substitute it over here, this is going to become like minus c sin x. Okay, plus c sin x is going to come. So this is going to C sin x minus C sin x is going to get cancelled. So you are going to get C. But what I want is I want 1. So therefore, in general, this is not, you will not get that the result need not hold for non-homogeneous ODE. Only for homogeneous ODE it will hold, for non-homogeneous ODE it will not hold. Means if I multiply by y1 is y is a solution, if I multiply by some constant, it is not no longer a solution for the non-homogeneous ODE. Okay, now let's go for the next theorem. Okay, so the next theorem you are having. Okay, so suppose okay, now we are going to say linearly dependent and linearly independent. So here what we are going to say linear dependent, linear independent is that suppose two functions are there, y1, y2 are said to be linearly independent on the interval a, b if their x is a constant. Okay, if their x is a constant, c1 and c2 not all 0. Okay, we are going to say what is dependent first. So we say that it is dependent. So we are y1. So let's take two functions y1 and y2. Okay, y1 and y2 are said to be linearly dependent. Okay, when do we say it is linearly dependent? If the x is a constant c1 and c2, okay, c1 and c2 not all 0. Both are not simultaneously 0. Okay, both are not simultaneously 0, such that this is going to become 0. c1 into y1 plus c2 into y2 is becoming 0. Okay, so in that case we say this is a linearly dependent solution. Okay, this is called linearly dependent solution or linearly dependent. If both are if it is not having, okay, if y1 and y2 are not linearly dependent, then we say that y1 y2 are linearly independent. So in other words, what we can say is that suppose you take any linear combination, y1 and y2 are there. Suppose you take any linear combination, c1 y1 plus c2 y2 equal to 0, then this implies what you need to prove is that c1 equal to 0 and c2 equal to 0. Okay, both should be 0. c1 equal to 0 and c2 equal to 0. If you prove that, if c1 y1 plus c2 y2 equal to 0 implies c1 equal to 0 and c2 equal to 0, then we say that it's linearly independent. Okay, this is another way of defining the same thing. So okay, so now what are the general solution, particular solution, and singular solution? So what is the general solution is, first we will see what is the general solution. So general solution means suppose y1 and y2 are two independent solutions, okay, of the given ODE. Then what you can do is that you can write any linear combination like this c1 y1 plus c2 y2. Okay, you take any linear, you take y1 and y2 are any two solution, and then take any two constants c1 and c2 and multiply that c1 with y1 and c2 with y2 and add it. Okay, so c1 y1 plus c2 y2 is called the general solution. Okay, where c1 c2 are arbitrarily, you can choose some constant. So then this is called general solution. Okay, I can write this as y equal to c1 y1 plus c2 y2. So this is called general solution. So if I choose some particular values, for example, instead of c1 y1, suppose I choose y equal to, let's say 2y1 plus 3y2. So I have chosen some particular constant, and this solution is called particular solution. Okay, so suppose you obtain one more solution, okay, something called singular solution. Suppose you obtain one more solution, let's say like which is not obtained from this general solution. We cannot obtain that from general solution. That is called singular solution. For example, you can consider the following ODE. It is a non-linear ODE, so it is possible. Mostly that for the linear ODE homogeneous, whatever you have. So in that case, you are going to get only the general solution format. We are not going to get any singular solution. So consider the ODE y dash square minus xy dash plus y equal to 0. So this case the general solution for this problem is that y equal to cx minus c square. Okay, and you can prove that another solution is also there, okay, which cannot be derived from this one. That is called y equal to x square by 4. So therefore, this is called this is a singular. This is actually I am giving an example for the first order only, not second order. So the first order you can see this one. Okay, so in first order you have y equal to cx minus c square, and second singular solution y equal to x square by 4. So this is not a linear ODE. Okay, this is not a linear ODE, and you can see that y equal to x square by 4 is a singular solution. Okay, now next one, what we are going to have, we are going to find, we are going to say basis which you might know already from your linear algebra courses, but we just revisit that. What is that? Okay, so you know already the basis means, suppose you have a vector space. Suppose you have a vector space. Okay, let's say it is a finite dimensional vector space. So in that case, what you can do is that you can find linear span. Okay, so you can find a set S such that S is subset of V, and you can prove that L of S equal to V. Okay. Second thing, what you can prove is that this S is linearly independent. Means what you need to do is that suppose this S contains n elements, y1, y2, etc. yn is there. These are the elements of this S. Okay, then what you need to prove is that alpha 1 y1 plus alpha 2 y2 etc. plus alpha n yn equal to 0 implies alpha 1 equal to alpha 2 equal to etc. alpha n equal to 0. This should be the linear span, means whatever elements are here, that should be linear combination of these elements. Then we say that this is a basis span. Same thing here. Okay, the basis we are going to define it over here. Suppose y1 and y2 are two solutions. Okay, suppose y1 and y2 are two solutions, and if we have any other solution, okay, not they are not proposed. Okay, the two independent solutions. So if you have any other solution, okay, if you have any other solution which can be expressed as a linear combination of this one, okay, then we say that this solution is a basis for the fundamental solution. Okay, that is y1 and y2 are independent solutions of AB. Then y1 and y2 are called basis of fundamental solution, because we are going to prove that if it's a second order linear ODE, then the solution, the dimension of the solution set is going to be 2. So that's the reason we are going to say if we found already two independent solutions, automatically that is going to become a basis for the fundamental solution. Okay, of course you got to prove that L of S equal to V, means I got to prove suppose S equal to y1 y2. Okay, suppose S equal to y1 y2, then I got to prove that L of S equal to V, where V is nothing but set of all solutions of the given ordinary differential, second order ordinary differential. Since it is the second order ordinary linear differential equation, you can prove that this is going to have only the dimension is going to be 2. Okay, the set of all solution is going to have dimension 2. That's the reason we are going to get this one. So, for example, once again you consider the ODE. So, y1 equal to sin x and y2 equal to cos x are two solutions of the for this ODE. So, can we find a general solution for this one? First question. Could you find a particular solution for this one? Again, that second question. And third question is, do you think they form a basis? Okay, that you have to answer. That means what you need to prove is that these two are linearly independent. So if you prove that, then you can do that. Okay, so that only thing you got to do. So what you can do is that you cannot generate. So for example, for linear ODE, what I need to prove? Suppose C1 into sin x, C2 into cos x equal to 0. Then you got to prove that C1 equal to C2 equal to 0. Or in other words, what you can prove is that can we express sin x as a linear combination of cos x? Means can I find some c such that sin x equal to c cos x in for all x in some interval a comma b? It's not possible. Okay, it is not going to exist. Therefore, they are linearly independent. Therefore, you are going to get that. Okay, so it is going to form basis also. Okay. The next concept is that suppose you have a suppose you have y1 and y2. Okay, suppose y1 and y2 are two functions given. Then we are going to define some concept called Wronskian. Okay, what is the Wronskian? Is that the Wronskian of two functions? Okay, y1 and y2 are two functions given. Then Wronskian of y1 and y2, this is differentiable also. Okay, Wronskian of two functions is going to be y1, y2, y1 dash, y2 dash. Or in other words, this is the determinant of y1, this matrix. Okay, in other words, I can write as y1, y2 dash minus y2, y1 dash. Okay, so this is going to be called as the Wronskian. It's called Wronskian because invented by mathematician. His name is Wronskian, so this name we are saying. So this is called Wronskian of y1 and y2. So for example, once again we take the same problem. Okay, y equal to sin x and y equal to cos x. So let us find the Wronskian of this one. So the Wronskian is going to be sin x. So this is y1, this is y2. So this is going to be sin x. This is going to be cos x, and this is going to be cos x. And this is going to be minus sin x. Okay, therefore this is going to become like minus sin square x minus cos square x. Therefore this is going to be minus 1. Okay, plus sin square x minus cos square x equal to 1. Or otherwise, what you can do is that you can just take other way. You can take y1, y2 are arbitrary you are taking, so you can take this one also. y1 equal to cos x. Okay, y1 equal to cos omega x. You take it. y2 is equal to sin omega x. You take it. Okay. So in this case, this is going to become like cos omega x sin omega x. Okay, and then this is going to become like minus sin omega x and cos omega x. So this is going to become like cos square omega x. So here one more mistake is there. So minus omega sin omega x, omega cos omega x. So therefore this is going to become like omega cos square omega x plus omega sin square omega x. Okay, therefore this is going to become like omega into cos square x sin square max. I'm going to take it inside, so that is going to become like omega because this is going to become 1. Okay. Same way, suppose I give another function. Let's say y1 equal to x square and y2 equal to x cube. Okay, then in that case also you can find. So this is going to be x square, this is going to be x cube. You can put 2x here. This is going to become a 3x square. Okay. So in this case, this is going to become like 3x power 4 minus 2x power 4. Therefore, it is going to become like x power 4. So this is the Wronskian which you can calculate.